Hello, in this mini video, we're going to show how to use the RFDBDES function. RFDBDES. So RFDBDES is concerned with the performance and robustness programs that we've been talking about. So in particular, we have a performance program. This is a general performance program considering everything we've been talking about. So it considers the transient control energy and the transient error energy. Alpha 1 then is a number between 0 and 1. When alpha is 1, then we're emphasizing the control F energy. When alpha, and in which case the error energy is not considered. When alpha is 0, then we're considering the error energy and not the control energy. So we have those two different things. Overshoot less than some number, undershoot less than some number, maximum control less than some number. We also have the robustness program that considers both noise and uncertainty. It uses another parameter alpha to indicate which is more important to us, whether it is the noise or the uncertainty. And again, sometimes it may not be obvious to you which one to choose, but you can, the nice thing about having a tool is that you can play around with these values and do what if scenarios. What happens if I set alpha equal 1, alpha 2 equal 1, or what happens if I set alpha 2 equals 0? You can investigate what happens in those cases. So here we present the tool RFDBDES. Okay, so we pass it an LTI object that is the continuous time plant. That continuous time plant may include a time delay, in which case the modified H transform may be used. We pass it the sampling period that we want to be working with. So it's going to do some sampling in here, and it needs that T to keep track of things. Then M is two values, M1 and M2. M1 is the degree, the number of coefficients of V1. M2 is the number of coefficients of V2. So this is for the performance, that's for the robustness. So this tells us how much degrees of freedom that we have. UM is the control magnitude. YM is the overshoot and undershoot constraint. So MP and MU go into YM. Alpha, so we have the two alpha values, alpha 1 and alpha 2. Alpha 1 is for the performance program. Alpha 2 is for the robustness program. And so we put those two into a single vector and they go in here. And the third, the last thing here is D. And D is something we use for what is called oversampling of the signals for performance. So you may have seen in some of the cases where you are working problems where when you do the optimization looks really good in discrete time, not so good in continuous time. And so, for example, you might set the overshoot to be some number. And when you actually go through and do the optimization, it comes out to be that you actually get more overshoot because in between samples, it might actually overshoot a little bit more than what you had in the discrete time. So what D allows you to do is allows you to do what's called oversampling. That is, in evaluating, for example, the overshoot constraint, because we have the continuous time system entered into this model, it allows us to look at values in between samples. And so in that way we can more accurately take into account overshoot, even if the overshoot occurs in between samples. And so basically what it does is it reevaluates, for example, the overshoot and the undershoot constraints. It reevaluates those according to the value D. So if D is 1, then we have the regular sampling. If you let D equal 2, then it will have in between each period there'll be two samples per period. You let it be 3, it'll be 3 samples per period. Okay, so 1 and then 2 in the middle. So generally speaking, or at least a rule of thumb, is that if you have an odd number in the middle, that works best. So for example, using d equals 2 is pretty good, or d equals 4. So in other words, an odd number, an even number gives an odd number in the middle. Okay, so 4 and together, you have the one at the beginning and then 3 in the middle. And so it's those are a good selection for D. So this allows oversampling of the signal. So that allows that. And so that's a nice little feature. I haven't shown you any specific examples of that, but you will come across examples where that happens. Well, let's look at an example of how to use this tool. So here's our actual plant. Okay, so here is this has a time delay associated with it. Notice that the nominal plant, so this is the plant that we think we have. And in this case, the poles are exactly what we're expecting. The gain is off, and the time delay is off. This time delay is twice this time delay. So we have a significant amount of deviation between the actual plant and the nominal plant. This is the plant that we're going to use when we do the control design. Here's our performance program. We're going to mostly emphasize the control energy, overshoot less than 10%, maximum control less than or equal to 5, and our robustness has an equal weighting between the two different costs. So we can go through and enter our system in like this. So here's our numerator, denominator, and then we enter the time delay. So here's where we actually incorporate the time delay into our LTI model. Here's the sampling period we use, and we're going to use these values for M1 and M2. Notice they're pretty large. Control magnitude is 5, 10% for error for overshoot and undershoot, and here are our values for alpha, 0.9 and 0.5. D is equal to 1. We're not doing any oversampling, and then we just plug those in here. Okay, our actual num A and den A. So here's our actual transfer function. Here's our actual time delay and the noise power. Here's the noise power we're going to use because we're actually going to have noise here. So remember, our robustness program included both uncertainty as well as noise. Okay, so notice the time delay here is this. Here's the actual time delay is twice that. Okay, so these are the values we use, and so by entering these values, we can then use this simulation diagram. So we'll calculate num1, num2, then C. Here's our actual numerator and denominator and our time delay. Here's the noise. The noise is going to use the noise power that we specified previously. And so this is the actual Y that is used for feedback. And here is, this Y is like a smooth version of this. So this is the version before the noise. This is the version after the noise. Okay, and so we have 3 scopes. One that looks at the control before and after the saturation. Here I have this scope that compares this signal to the. So this is the actual out. This is the actual output. This is the sensed or the measured output. That's what we have available for feedback. So we're comparing the actual output with the reference. And here's the sensed output. We'll look at that as well. So we get these plots. So here's our actual output compared with our step input. Here is our output with noise. Notice it has a lot of noise associated with it. And here's our control signal. We can see that our control signal is actually going outside the plus and minus 5 volts. And so because it does that, instead of being a nice smooth step response, we get this oscillatory response. Not very good. So here we have used M is equal to 14, and M1, V1 rather, has 14 coefficients. V2 has 25 coefficients, and we can see we don't do very well here, especially because our control signal is saturating, and so we've entered the nonlinear regime, and the system doesn't respond very well that way. So we end up with this oscillation caused by that nonlinearity. This oscillation has a name. It's called a limit cycle, and it's very common in nonlinear systems. It's actually a form of instability in nonlinear systems. So that's what we have here. Now I'm going to go ahead and change this number because it's really a robustness issue that's the problem. So we're going to change that to 100. And when we do that, we can see the output actually does settle, and it does hover around 1 pretty well. So again, if you look at the noise is quite large compared to the signal. So we're actually having to struggle with a lot of noise in the system. And here's the control output. Notice that the control is hardly phased by the noise. So that's a consequence of the robustness. Okay, it's a consequence of the robustness. So we can see that we actually do pretty well. And the important thing is we have a tool that allows us to vary the order of our controller in order to do that kind of thing. So that's really cool. So now in this case, we could use this block diagram because we know exactly what the guts are. Okay, we know what the actual transfer function is, we know what the actual time delay is, and so forth. So this is kind of a contrived example because we actually know a lot of stuff about the system, and we're just comparing what happens in the event that we have a mismatch between the actual and the nominal. But in practice, what you'll have is you will not have access to the guts of what the plant is. You will just have a plant with an input and an output, and so you won't necessarily know what the actual output is going to look like, because you don't actually have access to that signal. You actually get the signal that comes out after the noise. And so in general, you may need some kind of a filter to check for settling, for example. So to get rid of some of that noise for settling. Here I also did a couple of things. One is I used a pulse generator instead of a step input. So the pulse generator basically gives a series of steps. Step up, step down, step up, step down. And so you can investigate not only going positively, but going negatively. So here I also used FIR filters instead of the discrete filter. So a couple different things you can do. A to D and D to A converters are in the library that I gave, so you could use those if you want to investigate the impact of various resolutions on the system. So we have a tool to be able to work with a pretty complex system like this. Pretty complex system. So we have a nice, powerful tool that, again, uses the quadratic program and all of that machinery that we've developed in order to do this kind of thing. So we have a very powerful tool in this tool called RFDBDES, Ripple-Free Deadbeat Design. Thanks for watching.